Hello, this is Taylor Bacher, and this is my Lab 3 black hole. The purpose of this lab is to explore curving motion using Newton's law of gravitation and Newton's second law, and we're going to use computational methods to model these concepts. From this, the results were that the mass was found to be roughly 1.4 times 10 to the 34th kilograms, and the initial velocity was negative 2.95 e to the 7th and 5.4 e6, 0. A little introduction before we begin. For part 1, we want to find the mass of the black hole utilizing Newton's second law and the law of gravitation. We first need to find the net force, the position vector r, and parallel and perpendicular forces. Then we can use Newton's law of gravitation to calculate the mass. For part 2, we're going to find the initial velocity it takes for the spaceship to not hit the black hole or the planet. And we're going to use gravitation of both the planet and black hole acting on the spaceship, along with position and velocity update formulas. Part 1, Mass of Black Hole. To set up the code, we classified the star as the system and the surroundings as the black hole. We use a while loop to update position and velocity, and here we have initial conditions using my Georgia Tech email to determine the initial velocity and star trajectory. The mass of the star and delta t were given to us. From this computation, we found the average mass of the black hole. We also found the perpendicular net force, the parallel net force, and the gravitational force, all shown in their according colors. So what does it mean? Fnet and its parallel and perpendicular components equal the rate of momentum and its parallel and perpendicular components. However, momentum can be directly calculated using velocity and mass of objects. Fnet cannot be measured or observed. You can't find Fnet without calculating the rate of change of momentum. This means that the value of Fnet is deduced from dp dt. Part 2, Don't Crash. To set up the code for this part, we classify our system as the spaceship and the surrounding as the black hole and the planet. We use a while loop again to update position and velocity, and we add in both gravitational force from the planet and the gravitational force from the black hole. We use these initial conditions, and we find the initial velocity from trial and error. From this, we found that the ship does not end up crashing into the planet or falling into the black hole. The ship is roughly 1.9 e to the 11th meters away, and we also found the planet's orbital speed and orbital period. So what initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? We need to find the initial velocity through more trial and error, and then keep running the code until we see that it has followed the orbital of the black hole. We must ensure that the spaceship does not reach escape velocity, so it does not escape the gravitational force of the black hole. Here we can see the ship's speed x, the ship's speed y, and the ship's velocity. Some sources of error from these computations is that in part 1, we calculated the mass of the black hole using an estimated value. This is because it is an average, so it's not entirely accurate or precise. And in part 2, we use the same estimated mass again, but as not an average. So therefore, it's really inaccurate, and we also find initial velocity through trial and error, which is also extremely inaccurate.